Welcome to the deep dive. We take source material, unpack it, and pull out the key insights for you.
And today we're diving into compound interest formulas. We're working from an educational text on the topic.
Yeah, our goal is to see how these formulas work, why they're such a useful shortcut compared to, calculating step by step, and also look at some surprising ways they're used beyond just money.
It's pretty neat how a few symbols can describe change in so many different contexts.
So let's start with the basics. Compound interest. It's like simple interest, but the interest earned gets added back in, right? The principal grows.
Exactly. And doing that calculation repeatedly, say, over 20 years, that gets tedious fast.
Yeah.
The source really highlights how formulas cut through all that repetition.
Saves a lot of time. So what's the main formula?
Okay, for interest compounded once a year, the core formula is A1 plus R100N.
Right, let's break that down. A is the final amount.
P is the initial principal you start with.
Okay.
R is the annual interest rate as a percentage.
Got it. And N is the number of years.
Precisely. That formula gives you the total amount A after N years of that compounded growth.
So if you just want the interest earned, the compound interest, or CI, you take that final amount A and just subtract the starting P.
That's the simplest way, yeah. CI equals AP. The text also mentions a direct formula for CI, which is P times 1 plus R100 and 1. It's basically the same calculation, just rearranged a bit.
Okay, that makes sense. But interest isn't always yearly, is it? Sometimes it's compounded half-yearly or quarterly.
Good point. And the formula handles that quite elegantly. If interest is compounded more often, say X times per year.
Like X would be 2 for half-yearly, 4 for quarterly.
Exactly. You adjust two things. First, the rate R gets divided by X, because you're only getting a fraction of the annual rate in each shorter period.
Right, like half the rate if it's twice a year.
Correct. And second, the number of periods changes. It's not just N years anymore, it's N times X total compounding periods.
Oh, okay. So the exponent becomes N times X.
You got it. So the formula becomes A, P1 plus R x 100 and X. The source shows examples. And compounding more frequently, like half-yearly or quarterly, definitely bumps up the final amount. That X makes a real difference.
It's interesting how flexible that core structure is, and the source mentions you can use these formulas not just to find the final amount, but other things too.
Yes, absolutely. If you know some of the values, you can often rearrange the formula to solve for a missing one. You might want to find the initial principal P you'd need to reach a goal.
Or figure out the rate R you actually got on an investment.
Exactly. Or even find out how long, the number of years end, it would take to reach a certain amount. Now, solving for N sometimes needs logarithms, which is a bit more involved.
Okay.
But the key takeaway is that the fundamental relationship captured in that formula lets you solve these sorts of inverse problems.
And this is where, for me, it gets really fascinating. These formulas aren't just stuck in finance.
Not at all. That core growth formula, A, Pn plus R 100N. Think of P as a starting population and R as the annual growth rate.
Ah, so it models population growth over time.
Precisely. Or the growth in the number of, say, businesses in a region. It's the same mathematical principle of compound growth.
And there's a flip side, too, for things that lose value.
Right. Depreciation. Like a machine or a car losing value over time. The formula is very similar. Value after N years. Present value. 1R100N.
The key difference is that minus sign. 1 minus R over 100.
Exactly. It models value compounding downwards, decreasing each year. Crucial for businesses tracking asset value.
So it's a really versatile framework.
It is. The source even touches on how these ideas are the basis for more complex things, like calculating loan payments needed to clear a debt over time, which involves working backwards from future values.
So wrapping this up, these compound interest formulas, they look simple, but they're incredibly powerful tools.
Definitely. They help us understand how things change over time, growing like money or populations, or shrinking like the value of equipment.
And they give us that shortcut, avoiding all the step-by-step work. It captures the whole compounding process in one go.
Understanding this can really help you analyze financial choices, or just make sense of growth and decay trends you see in the news or data.
So here's something to think about. We've talked about money, populations, depreciation. What other things in life, maybe even in nature, might follow a similar pattern of compound change, even if we don't usually put a formula to it? Something to ponder.